If you feed a perfect mathematical equation with imperfect data, the entire system collapses. Early computing systems were built on the expectation of pristine signals, which made them highly vulnerable to the chaotic noise of reality. We call this historical baseline hard computing. Operating within these massive mainframes, the architecture relied on deterministic logic and rigid algorithms that required exact inputs to produce exact outputs. This approach works when every parameter is known and controlled, but outside of a highly regulated laboratory environment, perfectly clean data simply does not exist. This diagram illustrates the structural flaw. A classical hard computing system operates on a rigid binary step function, expecting a clean 0 or 1. When it attempts to process a highly fluctuating analog waveform from the physical world, the model breaks down. Because physical environments are inherently messy, these deterministic systems proved dangerously brittle in the field. Engineers needed a computational architecture designed specifically to process ambiguity. In 1965, a mathematician named Lotfi Zadeh proposed a solution to this flaw. He designed a framework that could mathematically process human-like vagueness, laying the groundwork for a distinct computational discipline. This methodology is known as soft computing. It is an architectural framework built around the explicit tolerance of imprecision, uncertainty, and approximation. The soft computing framework transforms uncertainty into a degree of truth, calculating results from data that classical logic would reject as an error. Mapping these principles is a step toward navigating the complexity of modern problem-solving. To see how this works, we will build a soft computing architecture from the ground up, starting with the mathematical reasoning of fuzzy logic and advancing to the autonomous learning mechanisms of neural networks. This chart visualizes a classical logic set for human height. The x-axis represents physical height, and the y-axis represents the degree of membership in the category of tall people. Classical logic dictates a strict binary limit, a harsh vertical step function placed exactly at 6 feet. Under this rigid boundary, an individual measuring 5 feet 11 inches registers a 0% degree of membership, while someone exactly 6 feet tall registers at 100%. The nuance of actual height is completely erased. Zadeh corrected this by replacing the rigid step function with the fuzzy set. Instead of bi-inclusion, the boundaries are generalized into a continuous curve, allowing for partial membership measured on a scale from 0 to 1. Plotting data along this new curve, a person who is 6 feet tall holds a membership degree of 0.8, while someone who is 5 feet 5 inches registers at a degree of 0.5. This decimal defines the mathematical degree of membership, a precise measurement of vagueness that remains distinct from statistical probability. By replacing rigid boxes with smooth curves, engineers created the foundational mathematical language required to process subjective ambiguity within a digital machine. Defining a set is only the first step. To make that data actionable, a system needs a computational framework to draw conclusions. In soft computing, this is the fuzzy inference system. Looking at the pipeline architecture of a fuzzy inference system, we see 4 distinct processing stages: fuzzification, the rule base, the inference engine, and defuzzification. These systems typically operate on one of 2 mathematical models. The Mamdani approach uses fuzzy sets for both inputs and outputs, while the Takagi-Sugeno model utilizes crisp, linear functions for its outputs to increase computational efficiency. To observe the pipeline in action, consider an automated controller designed to adjust a cooling fan based on fluctuating temperature and humidity data. In Stage 1, fuzzification takes the exact numerical readings from the hardware sensors and transforms them into fuzzy linguistic variables. A reading of 90 degrees Fahrenheit translates into a fuzzy tag like high. Next, the rule base applies human-like logic conditions to those tags, such as if temperature is high and humidity is low, then fan speed is high. The inference engine processes these conditions to generate a fuzzy output command. Finally, defuzzification reverses the translation. It takes that vague high command and calculates a precise mechanical value, outputting a motor control signal of exactly 2000 RPM. This sequential logic directly drives the anti-lock braking systems in modern vehicles. Rather than applying a binary on or off pulse, which locks the wheels, Fuzzy logic controllers make continuous, gradual pressure adjustments based on varying traction conditions. The fuzzy inference system serves as a translator, bridging the gap between chaotic environmental data and the precise mechanical actions a machine needs to operate safely. But the fuzzy inference system has a structural ceiling. The inference engine relies on a human programmer to manually write every rule. In high-dimensional environments with millions of variables, manual programming fails. To navigate genuine complexity, the system needs an engine capable of autonomous learning. This requirement led to the adoption of artificial neural networks, computational models structurally inspired by the interconnected neurons in a biological brain. In this standard architecture diagram, raw data enters through the input layer on the left, processes through one or more hidden layers in the center, and generates a prediction at the output layer on the right. The hidden layers perform the critical analysis. Each sequential layer learns to extract increasingly complex features from the raw input, identifying spatial hierarchies like textures, edges, and shapes without human guidance. The layout adapts to the data format. Convolutional neural networks utilize filtering layers to process grid-like visual data, while recurrent neural networks employ internal memory loops to analyze sequential data, like time series graphs or human speech. In generative adversarial networks, two separate architectures are pitted against each other. A generator creates new data samples, while a discriminator attempts to identify the fakes, forcing the system to optimize toward realistic outputs. By abandoning manual rule generation and routing data through layered neural architectures, machines gain the ability to scale their pattern recognition autonomously, which raises a mechanical question. If a programmer isn't writing the rules, how exactly does the network correct its own mistakes? The answer lies in the connections themselves. Each link between neurons carries an adjustable mathematical parameter called a weight, which dictates the strength and influence of that specific connection. Examining a single connection during a training cycle, known as the forward pass, data moves forward to generate a prediction. The system compares its prediction against the actual correct label. The difference between the guess and the truth is quantified as a mathematical penalty called the loss function. To reduce that loss, the network initiates backpropagation. The error data travels backward through the architecture, calculating exactly how much each individual weight contributed to the incorrect prediction. Using a calculus operation called the chain rule, the algorithm finds the gradient of the loss. This gradient tells the system the exact direction and magnitude required to adjust the weight toward a more accurate outcome. Networks pair this calculation with an optimization method called stochastic gradient descent, which updates these weights using small, randomized batches of training data rather than processing the entire dataset at once. Injecting this randomization prevents the algorithm from getting trapped in localized valleys of minor improvement, keeping the system moving until it locates the most efficient global solution. Predict an outcome, calculate the loss, and adjust the weights in reverse. This continuous optimization loop is the mathematical mechanism that defines machine learning. When you integrate the reasoning capabilities of fuzzy logic with the learning mechanisms of neural networks, you create a hybrid architecture known as a neuro-fuzzy system. In this unified model, a neural network acts as the optimization engine. Instead of an engineer manually drawing the membership curves and defining the rule base, the neural network analyzes the incoming data to autonomously tune the parameters of the fuzzy controller. We see the result of this synthesis on the factory floor. Industrial robotics operate in environments full of varying loads, changing friction levels, and sensor noise. A neuro-fuzzy control system processes these unpredictable variables in real time, executing exact mechanical maneuvers. As the scale of computation expands, the volume of uncertainty expands with it. The integration of big data and the Internet of Things is producing a highly interconnected landscape characterized by incomplete inputs and massive environmental noise. Rigid, deterministic programs cannot parse this level of ambiguity. Processing this incoming flood of messy data requires algorithms explicitly engineered to calculate degrees of truth. Soft computing provides the architectural foundation for these adaptive systems. By acknowledging that perfect data is mathematically impossible in physical environments,
It gives machines the flexibility to navigate reality.